Very happy to introduce Mark. He has been a software engineering manager at Microsoft for quite a while in the Synapse ML team. Okay, and now he's a PhD candidate in Bill Freeman's lab, and I had the pleasure of working with him and Andrew Zisterman and Bill Freeman on this work that he's about to present, which is about audiovisual grounding of language.
Well, thanks for the introduction, John. And also big thanks on this project that I was so fortunate to be able to learn a ton of different audio tribal knowledge from John. Like when you I'm a vision person, and when you enter into the audio world, there's a ton of different gotchas that you definitely encounter. And so John really helped steer us through this and eventually allowed us to get a paper done. So big thanks to him for not only organizing this, but also organizing this work. So yeah, today I'll chat a little bit about how we can create systems that learn language and learn the meaning of words without any kind of supervision at all, just from unsupervised data alone. And so to start, we'll play a little game. We're going to think about how can we learn language without any labels. And I'll start with a test. And so here's an example audio clip. And so this is of a non-human species. And does anyone know what that species is saying? Yeah? Kind of hard, right? But watch when I show the video. It becomes immediately clear. Yeah, so when you actually see this, it becomes clear that that's the penguin for damn it, ow. I'm like, ah. So there's really something to being able to see something alongside hearing it. That this extra modality conveys a ton of information and really helps you disambiguate what's going on. And the hope is that if you train with a lot of it, you start to discover the meaning of language. And I'll give you one more test. This one, I promise, will be a bit easier.
My pan's just started smoking. Touch of oil in, roll that round, and then just lay the steaks away, always away from me. And let the pan do the work.
So, even though you don't see this, because you understand English, you can kind of imagine and visualize this in your mind, what's going on. You might even be able to visualize the person who's doing the cooking in this video smoking. With that classic accent there. And so you're not that surprised when you see Gordon Ramsay cooking steaks.
Always away from me. And let the pan do the work.
The kind of idea is that this task of predicting what you're seeing from what you're hearing gets so much easier when you know the meaning of sounds, when you know the meaning of language. And so this is going to be the primary supervisory signal that's going to drive these networks to learn language without any supervision or otherwise. And so to give you a quick overview of what we'll talk about today, we'll first talk about the prior work, what people are doing in this field, and we really stand on their shoulders to build some of these architectures. We'll introduce a model called DenseAV, which tries to learn the meaning of language in just a purely unsupervised manner. We'll show some pretty pictures and examples. I'll whack you over the head with some bold columns here to really show that it works well. And then we'll talk about some ongoing work that we're really excited about in trying to understand what animals are saying to each other. So to start off, we'll dive into some of the prior work. And basically, this game that I played with you all in the beginning of the talk is just one particular example of contrastive learning. The idea is that you take a video stream, of which we've got millions and millions of hours of unlabeled video out there on the internet. You split it into a visual stream and an audio stream, and you tether audio and video together if they came from the same clip. And you ask the network to push apart audio and video if they came from differing clips. And the idea is that this is enough signal to really drive interesting learning and develop representations that are really smart and non-trivial. So one of the big ones that got released recently is ImageBind. This is sort of our main baseline and what we build off of. And so what ImageBind does is takes this to the nth degree and binds all sorts of different modalities into the image domain. So like audio, IMU data from head-mounted cameras, thermal imagery, text, all sorts of stuff. It bound into this visual domain. And it's kind of like one of these contrastive foundation models out there. But this is not perfect. It's not without its fair share of issues. So if we take a look at what ImageBind is actually doing, we'll see that it takes an image and a piece of audio. It featurizes them with a vision and audio big transformer backbone, and it spits out these tokens. There's spatial tokens that kind of correspond to different regions in the image, and there's also a special class token here in purple that kind of captures the global semantics of this particular piece of data. And the way that ImageBind is trained is that they just compare these class tokens in an inner product. And they train that for retrieval and cross-modal accuracy and things like this. And this yields a system that is spectacular at being able to pair together images and audio clips. It gets like 66% accuracy at 10 shots on a 1,000-way audio set retrieval task. An audio set, if you haven't worked with this data set, is like super noisy YouTube data. So the fact that it can get this style of accuracy is quite impressive. But you might ask, can it tell where that guitar sound is emanating from in the image? In order to do this, you can imagine, instead of inner producting those class tokens together, you take the class token of the audio and you inner product it with the spatial tokens of the image. A lot of times people refer to this as class activation maps. It's like a slight variant for this retrieval task. And the answer, when you do this operation, what do you get? The answer is not much. You don't really get anything. It doesn't highlight the key pixels. It really just highlights everything. So there's something missing here. Because we're only supervising these class tokens, it's not really getting the point that maybe it'd be a good idea to localize this kind of sound information somewhere in the image. And in order to promote that, we need to take a slight detour and think really hard about how to form this comparison operation between the image and the audio. And we're going to draw some insights from the broader vision community, who's discovered that max pooling, as opposed to average pooling, is this key operation that really promotes a localization of objects. So here, I'm going to take a brief detour and just show you a simple land cover classifier from a previous project we've done. It's like a big, fat transformer backbone. Average pools those spatial features together, does a linear prediction, and spits out some classes. Ordinarily, as vision researchers, when you want to see what the network is looking at, you swap the average pool in the linear layer. This is a no-op. It's the same exact mathematical operation. But now you can look at the predictions after that one-by-one convolution, aka a linear layer, and you get something that looks somewhat reasonable. But as soon as you swap that average pool for a max pool, you find that suddenly you get really, really nice localizations, because it's not incentivized to smear out signal all over the image in order to maximally activate that average pool. It's content with just leaving the information where it is, and the max pool will come and pick it out. So this is just a quick overview of a lot of different land cover classification interpretations, and you see that the difference between average pooling in the middle row and max pooling in the bottom row is really quite substantial. That suddenly the network localizes things in addition to just classifying them. And you get this more or less for free by just adding a max here instead of an average operation. And this is not something that's hasn't been done before in the context of audio-video separation. So this work is largely building off the work of David Harwath, this jointly discovering visual objects and spoken words. They form this inner product tensor and then take a max over the spatial dimensions and an average over the audio dimensions. And they find that they get really good localization of audio-video signals. And so something is missing from these modern ImageBind architectures that was discovered a few years prior in this DaveNet architecture from this paper. And so what our work does is really try to bridge the two, have these massive modern backbones and self-supervised losses, but also have these really high-quality localization properties. So with that, we'll dive into the architecture of DenseAV and see how it relates to this previous work, and also a bit about how it differs. So in terms of what we do here in this architecture, we take a video and we split it into its visual and audio components. We just take a random frame because it's good enough. We don't need to evaluate the vision backbone like 10 times in order to get something that works well. We pump these through paired backbones, so an image backbone and an audio backbone, and we get these densely varying features. So these are like actual features coming out of this network. They're PCA visualized, so instead of showing you a 1,000-dimensional blob here, I'm just showing you the top 3 PCA components as they vary across the image. And you can kind of see that the system like picks out different semantic objects and things and gives them a reasonable feature. You can almost see what it's learning just by looking at its features in PCA space. So it first featureizes these things and creates, one feature per batch of pixels, one feature for a few milliseconds of audio. And then what we do is we slam them together with an all pairs inner product. So every single spatial location, we slam it together with a location in the audio, and we get kind of a score for how much they couple together. That's their inner product. If 2 vectors are very similar, they're going to have a really high score. They're going to be very strongly coupled together, close to 1. And if 2 vectors are completely orthogonal, unrelated, they'll be 0, no score. And so here I'm just like visualizing that a little bit. You kind of form this volume where you've got these spatial axes and this temporal axis, and different parts of it light up. Whatever the network wants to do in order to be good at this task. And then finally, we max pool the spatial dimensions, average pool the audio dimensions, and pump this thing through a contrastive loss. And the idea is that in order to perform well at this matching task, it's got to come up with a bunch of really good couplings between an image and the corresponding audio clip. And that's the main form of supervision. We just give the network the ability to find these couplings. We phrase a loss such that it encourages the development of these really nice couplings. And then we just train it on a lot of data and see what it visualizes here. So that's kind of the high-level architecture, putting it all together. We featureize these images, turn them into features, pump them through to a contrastive loss. Some of the key differences between us and previous work are that we soup up our loss function using these modern contrastive losses like info NCE. This just allows you to compare like a single positive clip to like 10 or 100 different negative clips. So you get a really nice dense learning signal. We scale up our training data to be a combination of audio set and places audio. Places audio is like people describing images, and audio set are just like natural videos from YouTube. So you get a good mix of sound and also speech in this kind of training data set. And finally, we soup up these backbones. Like prior work had done more standard convolutional backbones, but we really wanted to see whether this would work in the transformer era. And in particular, we wanted to use completely self-supervised transformers, so things that have no human labels anywhere in the process, that just work by looking at these raw audio signals and learning from them. So in particular, for the visual side, we use Dino, which is a self-supervised vision transformer, and we use Hubert, thanks to John's suggestion, which is a self-supervised audio transformer that operates on waveforms. And in particular, we also add a few adapter layers. So these little things that can modify the features very quickly so that we can learn these via transfer learning. So our first step is that we learn these little adapters on top to just roughly get these 2 backbones speaking the same language. And then we fine-tune the whole mess so that it can get the most performance it possibly can. And it can pick up on very, very subtle cues that require rewiring the whole backbone. So yeah, that's kind of a quick overview of some of the tips and tricks that we use to get this architecture to work. I could probably fill up like 6 or 7 more slides with different various tips and tricks we had to do. So if you're interested in the gory details, you can reach out afterwards. And so now I get to reward you for sitting through that architecture presentation with some fun, pretty pictures and videos. So I'll first show you a few examples. What we're going to do is we're going to visualize that match map, that audio-video similarity tensor. And I'm just going to refer to these as activations of the network. And so we're going to visualize these in real time through various different videos. So
the elephant cools itself in the river. It watches the trees for predators.
So yeah, you can kind of see, I'll play it again, that as soon as the word elephant is uttered, the elephant starts to immediately glow. When the word trees are uttered, the trees glow. When water is uttered, the water glows. And we can kind of see this happening by looking at those deep features in PCA space. And you can even see them corresponding between the audio and the video. So I'll play this again.
The elephant cools itself in the river. It watches the trees for predators.
And so you can kind of see even there, just looking at the high level of the audio, the purple elephant is shared between both the audio features and the image features. The river glows yellow in both audio space and video space, and trees glow blue here. And so this is just like one quick example. Here's another one.
Cut the peppers on a wooden cutting board.
And so you can kind of see as soon as the word peppers is uttered, those peppers glow. Wooden cutting board, it gets adjectives, it gets things like this. There's plenty of blind spots in the data, like it doesn't know what a fork is, because I don't know, there wasn't enough people talking about forks, but at least on the high level, it gets a lot of different nouns and even some adjectives in there. And interestingly, it doesn't just work for like detecting the meaning of words, but it can also localize sounds in images. So here's one classic example. Yeah, and so this is just one example of like every single time the saxophone plays, that thing glows. It's a little bit more flaky for sound than it is for language because it's just a harder signal to associate. There's just a lot more ambiguity, but when you train on a large enough data set, it starts to pick up on both kinds of audio-video correspondence. And we'll see later in the talk how this can be refined and probed in order to get even more interesting kinds of results. And so this is just some static examples to show you in case the video is a little bit tough to see. So here I've just taken an image and I've spoken different words, and you see that different components of that image light up. This is in contrast to just taking that class token and slamming it against the visual tokens. So it's not just looking at the key object, it really picks out individual objects. And if you say things that aren't there in the image, nothing will light up because it can't find any correspondence. It really needs to think about what are the Platonic forms in each of these modalities so that it can find a really reasonable match. So if you say the word elephant, it's not going to find any couplings there. So it's also robust to these like negative example kind of things. And so you had previously seen that it works for both sound and language, but one of the follow-ups we did is to really try to disentangle those two things. There's a difference between a dog barking and the word dog, and clearly the network can understand both, and we really wanted to see, can it not only understand, but like disentangle and separate these two kinds of correspondences without any sort of supervision. So if we go back to the key architecture here, what we're going to do is we're going to slightly generalize this by adding multiple different kinds of feature heads. So in particular, we'll take those original 1,000-dimensional features and we'll split them into two 500-dimensional feature maps corresponding to two heads of features. And then we'll form two of these audio-video activation maps here. I've overlaid them. One of them is highlighted in red, and one of them is highlighted in blue. And we'll take a little page out of the book of this idea that max pooling promotes localization in space, and we'll max pool those two heads together before pumping it into the final contrastive similarity loss. And so just giving the network the option to kind of organize itself, giving it two channels of information upon which to find these audio-video matches is enough to start pulling apart sound and language. So here's a quick still example here of looking at these activations across these different heads in the network. And you'll see head one, it just chooses one head at random to kind of pump its sound into, is the sound head in this particular training seed. And so it's going to light up when the dog barks, but it's not going to light up when you say the word dog. And head two, in comparison, in this particular seed, just decided to be the language head, and it's going to light up on things like red shirt and baseball hat and the actual word dog. And so this decomposition just happens naturally when you train it, which is a really delightful emergent property of these massive networks. And I'll caveat saying that we added a slight amount of regularization just so that these two things didn't light up at the same time, but that regularization didn't really rely on labels or anything like that. It just kind of encouraged orthogonality between these two different heads to really just clean up that signal a bit. And so I'll show you a quick video example here.
It's okay, puppies. It's just the snow.
Yeah, and so this, it's kind of, I'll play it one more time just to show.
It's okay, puppies. It's just the snow.
So you can kind of see that when the dogs are barking, all the dogs glow blue. When someone says the word puppies, the dogs glow red, corresponding to the other head of the model. And when the word snow is uttered, the snow in the background glows red, corresponding to the language head. And you'll also see one key limitation here, which is that when you just train with one frame, it's going to learn like semantic correspondences. It's not necessarily going to be able to localize individual puppies that are barking. You know, if you train with more than one frame, it can get smarter in that way. Or if you train with motion and things like this, it can start picking out individuals. But as of now, it's largely like a semantic matching thing that this kind of architecture learns. Cool. So that's a quick overview of the architecture that we had built, and now we'll hit you with some bold columns and tables and things like this, just to show how it performs and how we evaluate this kind of a system. So, you know, the simplest way to evaluate these kinds of systems, these cross-modal contrastive learning systems, is retrieval. So we take 1,000 different classes, 1,000 different examples, split them into audio and video, and then try to match them up. Both from image to audio and audio to image. And we showed that this kind of fine-grained matching strategy allows the network to kind of look for matches in a way that just slamming together a single class token does not. So it can help on retrieval, but we're less interested in retrieval. We're more interested in the learning of language and whether we can actually pull out individual objects and things like this. So we needed to make an evaluation data set to really probe and understand what this is learning. So in particular, we created this speech-prompted semantic segmentation data set by taking images from the ADE20K data set, which is a really painstakingly labeled by Antonio Torralba's mother data set of thousands of images, perfect pixel annotations of different classes, something only a mother's love could create. And so that's got this really nice semantic segmentation maps. And we can then take an object, say a large object like a tent, and just highlight that. Say, like, that's the label for the tent. You get a nice, precise semantic segmentation of that tent. And you can also just speak words. You can narrate what object you're looking at. You can say a picture of a tent. And we can do this with synthetic speech so that we know exactly where the word tent is in this particular utterance, in this particular prompt here. So this is a data set of kind of 3,000 or so pairs of these image audio prompts where the image is perfectly highlighted, the actual word that refers to that object is perfectly highlighted, and then you can use this for downstream evaluation to kind of measure how well these two things are aligning. And likewise, we could do a very similar thing with sound-prompted semantic segmentation. Take that same ADE20K data set, pull out a cow in this case, and then prompt the network with the sound of a cow mooing. Here I'm going to use random cow sounds from VGG Sound because it's a very nice high-quality sound data set, relatively high quality. And here we have a little bit less because there's less correspondences in the sound space, but we've got about 106 image object pairs that we can use for evaluation. So this is kind of what some of the various different speech and sound prompted semantic segmentations look like. Up on the top row, I've got some images. In that second row, I've got DaveNet, one of the key baselines here. And the second to the last row are labels. So this is what our speech and sound prompted data set actually assumes is ground truth. And the second from the bottom is DenseAV. So you can kind of see that, when you say the word iceberg, the iceberg really glows, and it just highlights only the iceberg, which, makes for a nice correspondence to that iceberg label coming from ADE20K. And so just to highlight how we're actually doing this evaluation, we take this image of a tent and the audio of a tent, we feed them both through DenseAV to get that nice heat map over the particular example for the word tent, and then we compare it to that label. And thankfully, it's just a binary classification task at this point, so you can use things like map and MIOU and also like average precision and things like this, so that you can evaluate this without any dependence on thresholds or where the actual activation is between 0 and 1. It's kind of a nice threshold agnostic way to evaluate these kinds of systems. And so this is where we can see a nice large bump in these metrics for speech and sound prompted semantic segmentation over an approach like ImageBind, which kind of really doesn't perform a lot of semantic segmentation when you probe its inner features. So that's just like a quick high-level overview of some of the things that we discovered in this analysis. Moving on to some ongoing work. We started out this work not for understanding how humans learn language. I mean, that's like very interesting and very useful, but we really wanted to build something that had the possibility of being able to translate animals, something where there's absolutely no labels out there for you to use and understand. So having a system that's completely unsupervised is absolutely critical here. So we've partnered with the Wild Dolphin Project. They gave us like 30 years of video that kind of looks like this. It's a little bit hard to hear. You can kind of hear something there. Yeah, there's like some slight whistles in here. It's hard to hear over the conference audio just because it's like very high frequency, almost just out of range of human hearing. But these dolphins are like consistently whistling and squeaking and squawking and making these different sounds. They're communicating with each other. From talking with the dolphin researchers of the Wild Dolphin Project, they have names, they have different kinds of behavior, different kinds of vocalizations for things like hunting, for things like intercourse. They've got a pretty rich auditory system in there. And so that's the kind of data set that we're now working to apply DenseAV to. We've got some preliminary analyses that show that on not just dolphins, but broader cetaceans, systems like this can learn like interesting features. So I'll briefly show, this is an example spectrogram from one of these data sets. It contains a few whistles here. Let's see, are you able to see? A few whistles here, and also some various different like clicks and clacks that kind of show up as more broadband noise here. And when we take these deep features coming out of these big foundation models and we look at their top principal components, in the same way that you saw in the visual principal components, like different objects pop out as different colors. This one, the first three principal components are like automatically detecting when there's useful sound in this signal. This is super useful because these kinds of data sets have a ton of silence as they're just like passively monitoring huge swaths of area. And as you go deeper into the principal component space, different objects start to pull apart and show themselves. And so this is PCA 6 through 9, and you can kind of see that the core click trains, those big broadband signals that are over here, they light up as orange in PCA components 6 through 9, whereas these whistle signals over here, they're going to light up as white in PCA 6 through 9. So what it does is it hints that these systems are starting to like parse and separate various different components of these animal language signals. Some of the analysis we've done shows that it can roughly start to delineate species. So this is an example of these features trained on large corpuses of whale sound. I've highlighted the orca species in blue points and the humpback species in red points, and they can start to roughly cluster these things in an unsupervised manner so that researchers A, can start to identify these species just on their audio signatures, and B, if they're discovering this structure, the hope is that they discover a more interesting substructure in each individual species that we might be able to associate back to visual signals or other kinds of telemetry signals, like where they are, what are the individuals, what are the biologists think they're doing at that given time. So yeah, that's where we're going with this. We just got this data, so we're still pouring through it. If you're interested or you work in this field, definitely feel free to reach out. And with that, I just want to thank everyone, thank the conference organizers. If you're interested in learning more about this work, we've got a little website, got some fun demos that you can click on and play with. And you can also find my contact information there if you want to reach out. So yeah, thank you all. Happy to.
So we have time for questions. Anybody have one? Yeah, back there, could you maybe approach the mic? And if people have questions, if you could go towards the mics, that would be great. Yeah, Jonathan's going to bring a mic around. But
thank you very much. Very nice work. So my question is, the last videos show that the dolphins, perspective, but the signal and the, visual information. So the first task is people can see the image, and we talk about that's the scene. But the last experiment setup is actually totally different perspective to capture scenes. And the dolphins speak about totally different things, right? So how to align the dolphin speech with that just context of the, overview of the scenes.
Yes, yes. No, those are like fantastic questions. Just in case anyone didn't hear the question, it's like, well, dolphin world is so different from the human world. They don't have nouns. They don't do the same things. Also, it's just going to be a lot harder. You didn't even mention this, but there's a lot of other challenges too, like multiple dolphins. The fact that these dolphin signals can carry for a really, really long distance, so you get a ton of different chatter. They're almost always in these pods of like 8 to 15 dolphins at a time. So it's really hard to localize. The Wild Dolphin Project has some like microphone rigs that they're testing out, but still they haven't been using that for 30 years. So there's like a ton of challenges with this animal data, and it remains to be seen whether we'll be able to do it for the visual signal in dolphin communication. I think that there's not a huge amount of nouns in dolphin world, not like we have in our world. So it's going to involve something that takes into account a little bit more temporal information, and maybe just uses these biological annotations coming from researchers to try to, find something for these systems to latch onto in the audio. And also, I'll briefly call out that, DenseAV was trained with like a combination of people talking about things and also just raw visual signals coming from plain videos. And it will also yield like similar kinds of discovery of nouns if just trained on the raw audio, the raw videos coming from YouTube as well. But even YouTube videos, they're a little bit more curated than just like random videos of people talking in the hallway and things like this. So the dolphin data will be very, very challenging, to say the least. So if any of you guys have good ideas for other animals, other domains where you can really associate these two signals together, I'm all ears.
okay, who's next? I saw this question earlier, so.
Oh, thank you. Nice work, thank you. One question that is for me is Places audio dataset that you use for training has a very clear speech.
Yes.
It's like extremely high quality, and there's a still image. Places dataset itself is just image dataset, and those are also quite high quality, but like speech kind of induces language here. I was wondering, like, how do you see this problem? Like, do you see this model as a speech vision model, or is it also capturing environmental audio? Because like Places audio is like, of course, people are reading from some caption. That's how they prepared Places audio dataset. There's a clean caption, and somebody speaks that. And it's like kind of language vision training.
Yeah, no, that's like a great point. This Places audio data set is definitely clean. And so that's why we needed to add audio set to really give it access to dirty audio, environmental sounds, and audio set is what's going to drive like most of its sound localization capabilities, and it will likely drive some of its robustness too. So in the paper, we have some analysis of like corrupted with noise examples and showing that like these results still hold up even if you blast these things with noise of various different amounts comparable to the signal. So, I think that large-scale training and adding in additional video data sets really helps, not only for robustness, but for sound localization, things that you don't get by just hearing people talk. Yeah.
Okay, I think there's some questions in the back. Oh, one person already has a mic, so please go.
Hi, so very nice work and amazing talk. Thank you. I have two questions. The first one is you have talked about the benefits of max pooling, and you use max pooling in the visual modality. But on the other hand, on audio, you are doing an average pooling, so I wonder why.
Yeah, no, that's a great question, and one that can only be explained with the classic graduate student descent algorithm, where we tried it. We really tried it, and we tried all sorts of different variants of this. Like we even had these methods that could interpolate between mean pooling and max pooling, and it just often when you give the algorithm the choice between mean and max pooling, it'll choose to mean pool because that's easier. But the max pooling really forces it to localize, which I think is a harder task. For the audio, if you think about max pooling on both dimensions, you get a very sparse gradient. Only one slot in your tensor is going to be getting that positive learning signal gradient. And all the other slots are going to be getting, not this kind of just background negative signal. So part of my intuition about why you still need some average pooling in the mix is that it allows gradient to flow to a few more places in there. We had also done some interesting things on annealing this, so training first with average pooling and then starting to bring in the max pooling. We weren't able to get spectacularly different results with that, so we just kind of kept it simple and chose this particular blend. But certainly I think that this particular aspect of the architecture is one where future work can make a lot of benefits because it's a large operation. You got to slam together a lot of vectors, and this can be done with an einsum. But when you're doing it across positives and negatives, it's also just kind of computationally difficult. So there's certainly, I think, more to be said about that max and average pooling. But that's the best we could do in all of our experiments. So.
Okay, and the second question is, you were showing some audiovisual similarities in both positive and negative examples. Mm-hmm. Were you using any thresholding there?
What do you mean by transcoding?
Thresholding, so you were...
Oh, thresholding.
Yeah.
No, so that's basically just, well, maybe I should say that there's one regularizer in here that kind of encourages it to be quiet when it sees, spurious correlations in the negative example. So implicit in the training is just a slight regularizer that says, don't use negative activations to model things. Model positives, don't model things that aren't there. And so that, I think, helps kind of make these things bottom out at 0 so that when you plot them, you don't see big negative amounts of activation. And I guess in these particular examples where just using a global color map across all the examples so that these ones kind of, when they're 0, you don't have one pixel in the image that's red just because of the fact that it's the highest one of a lot of very small pixels.
Okay, thank you.
Okay, is there another question ready? Okay, yes, lined up at the mic.
Regarding the encoders that you're using, the deep DenseAV, I saw that you use a Dino. Dino is a vision transformer.
Yep.
It contains the language information or the textual information in it. And I also see that you're using Hubert as your audio encoder. But Hubert is a self-trained model which doesn't use any textual information. Do you have any comments on if I use a textual audio encoder, or textual related audio encoder, for example, it's a supervised trained model. For example, I use a whisper model or a whisper encoder. Would that be any thing on your research? Yeah.
Yeah, and just to clarify, that Dino isn't trained with any text. It's totally self-supervised based on a contrastive learning scheme on crops. So that's why we chose it. Both of these backbones we chose because there's no text anywhere in the loop. but I think certainly you can improve if you use a backbone with text. Like, we really wanted to make something that could potentially work in an animal domain where there's no text, but using clip, you can get pretty reasonable results. You got to do a few things to clip to make it really nice. Whisper, I think definitely, if it was around when we were working on this, we would want to use something like this, because Whisper just has great features if you use them. Often they just like linear probe exactly what you want right from the get-go. It knows about kind of sound and language. So definitely, if you're going to remake it, Whisper is a very good option as a backbone.
Because when we saw your examples, when the cars or trees are highlighted or activated, they're linguistic clues. This is what you found.
Yeah, and I think that certainly with Hubert, because it was trained on like Libre speech, it knows a lot more about speech than it does know about sound. And we had a lot of trouble when we were making this that, in vision, there's these foundation models that are just like omni-visual systems like Dino. It's just trained on a lot of images from all over. But at least when we were working on this, there wasn't something that was just trained on like a ton of audio in a self-supervised way. And so, if we use something trained on audio set, we found that it had great sound localization, but suffered on speech understanding. And if we use something trained on speech, we found that it could at least do some amount of sound localization. It wasn't as good as, say, if you used like a backbone that was totally trained on audio set. So we had to make some trade-offs here to get it out the door. We found that it was easiest to take Hubert, which is trained on speech, and give it, through fine-tuning, some amount of sound recognition capabilities. Like, that sound recognition capability really comes from the stage in the architecture where we fine-tune the full weights of the backbone. Like, you don't really get good contrastive sound discovery with just Hubert alone. You need to fine-tune it in a particular way.
So we have a little less than 2 minutes left, and I see a number of people lined up for questions, and I would love it if we can... Oh, that's the end of the talk. Oh, okay. So we have 7 minutes. Okay, excellent. So keep going with long answers, and we'll be able to get through the people who kindly stood up to ask questions. Go ahead.
Hi, Mark. Interesting work. I'm interested in your dolphin sound ongoing work, especially because in California we had mapped about 800 sites in Sonoma County for bird sounds. And so I have some higher level questions. And so the first one is, do you see the challenges of sounds which are not dolphin sound? Well, not dolphins, but similar sounding. For instance, in our case, we had American robin and black-headed grosbeck, like sound so similar and difficult detecting and separating them. Second one is, what kind of input would you see is ideal, like a spectrogram versus an end-to-end waveform model? And third one is, obviously, as you mentioned, there are some, these sounds obviously are above our hearing range. And so how are you going to use that information, because that's useful at the end of the day?
Yeah, no, great questions. Maybe I'll do the easy ones first. Above the visual range, yes, we, even though these models like, Hubert and Whisper, they're trained with human speech, you can kind of take these high frequency things and just tell the network that it's sampled at a lower frequency. And the upshot of this is that it kind of plays it slower and it plays it within your hearing range. Like, these whale and dolphin sounds sound like ghostly flute songs and things like this when you do this particular transformation. So this helps these models that are trained on low frequency data understand high frequency data, because it just shifts it into the human register. I think number two, sorry, what was number two again?
I lost track myself. So, yeah, similar sounding animals. Yeah, similar sounding animals, and I think, yeah, spectrograms versus end-to-end.
Oh, spectrograms versus, yeah, that's an easy one, because Hubert takes waveforms. I think some of the newer models take spectrograms and things like this. I think that it really depends on what backbone you're using. I would say pick a really good quality backbone and then just use what they use if you were just starting on this kind of research. And then the first question about distractor sounds and mixtures of sounds. So this is like a very reasonable question. I mean, DenseAV just assumes like one track basically, but you can probably scale this up to multiple tracks without it really changing. You can try running sound separators prior to doing this to, isolate individuals. And, this is something that will certainly plague the dolphin data, because the way they collect this is that they're all on this dolphin boat, this Stanella, and they're boating around, they see some dolphins, they jump into the water with snorkel gear, GoPros, and hydrophones, and they swim after them, but these dolphins are like booking it. And so they gotta move the boat to keep up with, for safety. So throughout this kind of audio, you'll hear the boat turning on and off, you'll hear the bubbles from the snorkels, you'll even hear Denise, the main researcher, like kind of cooing with the dolphins and talking with them. So it's a very challenging data set with a lot of these distractor sounds in there. So this is another avenue that we're pursuing of like, how can we get something where you can just isolate dolphin communication and just focus on that, because that's going to be really necessary to making sure this thing is robust, because I don't know, these big fat networks take so much to learn and a lot of careful data. So.
Okay, so maybe now it's time to speed up a little bit for the last 3 questions.
Thank you very much for the great work. It's very interesting and ambitious. I think there are many technical challenges, but I think one of the most difficult challenge, in my view, is on the audio side. Audio is polyphonic and is also very diverse. I know you have mentioned this. The audio model you are using is Hubert. It's trained on speech, which is monophonic and very constrained. But the problem you're trying to deal with is general audio visual scenes like dolphin sounds. General sounds may have a lot of events active at the same time, and dolphin sounds are very different from speech, from general sound events that we have in the audio set. So how, in the future, how would you address these issues? Would you like to, for example, incorporate source separation mechanisms in the audio models, or maybe, extend the data set from audio to train more powerful audio foundation models to deal with dolphin sounds?
I think yes and yes. That separation, I think, will be a critical stepping stone, and also, retraining these foundation models so that they understand the underwater signals much better. I mean, that so much of the shoulders that we stand upon are these massive foundation models that are almost there and just need to be aligned. And so, it's going to be critical for this next stage of research that we build new foundation models on even interspecies, all the species, just the most data you can possibly throw at this kind of stuff.
Okay, thank you.
Okay, next question, please.
Okay, many thanks for sharing. My question is that we can imagine that there will be a very simple and straightforward pipeline for doing the similar things, that we can use audio tagging or audio caption model to generate a caption or tag for the query audio, and use the text query like segment anything to do the audio query the segmentation. Have you ever compared your methods with this very simple and straightforward baseline?
So is the question comparing the method to this idea of captioning and then associating?
Captioning audio and use the generated audio caption to and text query the image segmentation model to do the whole things.
Yeah, no, we didn't evaluate that. We sort of constrained ourselves to think about these models that had text nowhere in the pipeline. In general, if you use text, everything gets a lot easier, because you can use an LLM, you can use these things. It's just so easy to associate text and image. So I would assume it would do better than just audio alone.
Okay. And my second question is that, do you think if there is a risk of this model to learn a spurious correlation? I think there may be twofold. One fold is the spurious correlation from the context. And second fold, and I see that your trained data is a still image, but sometimes the sound happens happens during the interaction between the two or several different objects. So there must be some spurious correlation between the still image and the interactions. Do you think is a way to elevate this issue?
Yeah, I mean, you definitely can see this. You can take one look at our regularizers page, and you'll see a little bit of this fight against these artifacts. in general, like the negative samples and contrastive learning help to push down those spurious correlations because, if you start correlating with something that doesn't really like statistically hold up, you're going to get whacked by those negative samples. The second thing is kind of these systems, they can understand correlations even if it's like, you see a dog in the first frame and then you say the word dog later. So long as, because if you're randomly sampling frames from these movies, it kind of all comes out in the wash that it just wants to represent what is in that particular clip so that it can possibly match with something else. And so, what we find is that even though we train it on single frames, if you featureize all the frames and featureize all the audio and look for correlations, you can get these correlations even if they're very separate in time. Even if, there's a dog and then 5 seconds later, a person will refer to the dog. And kind of it comes down to the idea that it's this factorized model. It's got features for audio, features for the visual stream, and those features are kind of platonic about the objects that they're seeing, and so it allows for correlations across time. I don't know if that answered your question, but hopefully it kind of spoke.
I think we're running out of time here, and it's time for the next speaker. But let's have the last couple of questions really quick.
My last question is that there's a very small point that I'm not sure if these methods work for the different microphone. As you know, there's a tag for the speech assistant that's like Alexa. They use a very ultra high frequency sound, and this high frequency sound can, because the design of the circuits, the microphone can receive some of the low frequency signal. Yeah, especially when you're talking about the dolphin, there's also a tag named the dolphin tag to use ultrasound to generate a low frequency sound from some specific microphone. So I'm wondering if you test a system on the different kind of microphone system to test its robustness.
Yeah, so I think what you were saying is that do we have to use a different microphone system for dolphins? And the short answer is yes. You need to use this underwater hydrophone that records at 196 kilohertz. So it is like a separate kind of thing.
I think we just have time for one more question.
This is cool, thanks. I was wondering, what is the extent to which that your model learns that most objects have, you can refer to them in multiple ways, right? Like they're synonyms. So for instance, in the example that you showed with, cliff, positive, what if you put in mountain or something that's related? Does it learn those semantic spaces, or is it very tied to the exact word that the thing was presented with?
It seems to learn semantic spaces, puppies in the example and dog and things like this. Part of that might be because it just sees these things in the data set, the word puppies, the word dog, the word barking. And part of it also is that it's trying to map to this shared semantic space where it can perform these queries efficiently. And you see in word embeddings and things like this that dog and puppies and husky, they're all kind of the same feature. And it's sharing that quality of representation amongst all the words there. So I think a similar thing will happen in these kinds of models where as they're trained with larger and larger data sets, it starts to really group synonyms together in a meaningful way in the feature space.
Nice, thanks.
Thanks for the lovely questions, you guys.
Thanks a lot, everybody. Yeah, please thank Mark.